For this week's Ethical Dilemma in Science, I decided to go in a slightly different direction. Just finished my 5-mile run today. It's like one of the hottest days of the year so far. So lucky I was able to do it on a treadmill at the local gym. I'm thinking about how much I appreciate the ability to have a nice ice cold water at the end of my run. So for this week's Ethical Dilemma in Science, we're going to take a look at, who has access to water, who has access to ice water, and different considerations related to that. Under ideal circumstances, everybody would be able to enjoy a cold glass of water on a hot day. And that's important because our human bodies are made upwards of anywhere from 65 to 75% by weight being water. If we would die basically within about 3 days, depending on conditions, without access to water. And so we see that water is very, very important to us. If we take a look at the water on the planet, about 71% of the surface is covered with water, but the vast majority of that, over 96.5% of the water on the earth, is salt water, ocean water that we can't drink. That leaves about 3.5% of the water on Earth that is fresh water, but about 2/3 of that is going to be trapped in ice and glaciers. A small amount of it is going to be in the atmosphere, but basically just less than 1% of the water is available for us to drink. And so in many cases, and the slide illustrating here, a tank of non-potable water is basically non-drinking water. So the ethical dilemma in science for this week is focused on, is it ethical to drink ice water? Recognizing that some of us have ready access to clean drinking water, but on many areas of the world, they do not have that same access and privilege. So the goal of providing water to a population is to provide potable water, to basically provide drinking water coming from either a surface source like a river or a stream or a lake, or a ground source like a well, in which the water has been treated to meet some type of standards for consumption. And so that mainly means taking the water and treating it to eliminate microorganisms, bacteria, toxic chemicals, viruses, fecal matter. If we take a look at this infographic from The Guardian in 2017, we can see that the countries in dark blue, like Canada and Greenland, countries here within Europe and Australia, less than 1% of the population is getting their water from these unimproved sources. But a country like us, the United States here in this lighter blue, we've got anywhere from 1 to 10% of the population which is not having access to improved water. Worldwide, this becomes an even bigger issue as we take a look at areas throughout Africa and Central Asia, some of the Polynesian islands over here, where we see that upwards of greater than 30% of the population is getting water that is contaminated in some way. If we take a look at this worldwide, about 2 billion people, about 1 out of 4 people worldwide, is drinking water that is contaminated by feces. And this contributes to huge risks in drinking water safety. This contributes to about 500,000 diarrheal deaths per year, as well as other chemicals which may be found in the water that have other long-lasting effects on health of the individual. Further illustrating the privilege that we have in getting access to purified, treated water for drinking, we can pull up water quality reports. And so this is the water quality report for Glenside. And so it goes through, talks about where the water is coming from. So in this case, we've got water coming from a variety of creeks, the Schuylkill River, taking a look at this, contaminants that may be present in the source of the water, taking a look at it, and then they've done chemical testing to give you an indication about what is present within the water and whether or not it's at safe levels. And so it goes through, and it's got a variety of contaminants, inorganic, radiological, volatile organic contaminants, kind of going through. And what we can see is that none of the water things that are being tested for, the chemicals that are being tested for in our treated water is at a risk for concern, indicating again that we have access to good quality water in the United States, especially in the area around campus. So in addition to getting access to high quality drinking water, we also have the advantage and the privilege of having that water delivered to us. When I fill up my water bottle at the gym, I go to the water fountain and I put the bottle, and it's got a thing for refilling the water bottles there. Directly, as opposed to purchasing a plastic water bottle and kind of using it once and then hopefully tossing it into the recycling. If we take a look at worldwide, roughly about 1.8 billion people live in households without water supplies to the premises. So just under 1 out of 4 people in the world have to go someplace to get their water. About 1.2 billion have basic water services, so they can get to an improved water source with a round trip of less than 30 minutes. And so basically to get water, you've got to go someplace. About 280 million people have to travel greater than 30 minutes round trip in order to collect water from a source. But in addition to that, about 500 million people, almost 500 million people, are taking water from unprotected wells, springs, and untreated surface water. And so they're collecting water, kind of illustrated on this slide here, by going down and collecting the water in the same location that people are bathing. The same location that people are doing laundry and doing dishes is where they're obtaining their drinking water, in which they then have to collect that and then carry it back to their homes. Further complicating this question is the fact that, I like ice cold water. The idea of refrigeration. A 2018 International Energy Agency report said that refrigeration and cooling corresponds with about 6% of the world's energy consumption, and that's expected to rise going into the future. And so there are chemicals involved with this. Hydrofluorocarbons are a current refrigerant. And they have the risk of acting as a very potent greenhouse gas, much more warming potential than carbon dioxide if they leak into the atmosphere. And so they're better than the previously used chlorofluorocarbons, CFCs, that were very destructive to the ozone layer and have been phased out. But any of the refrigeration units have the risk of causing damage to the environment because the chemicals that they use could get into the atmosphere and affect the atmosphere. So the way that refrigeration works, whether we're talking about refrigeration to cool your homes with an air conditioning unit or freezing of ice within your refrigerator freezer, is this idea that we're going to be taking that refrigerant, we're going to be taking a chemical, putting it through a series of pipes, and basically allowing it to pull heat out of one of the sources. And so in this case, we're going to start here with a compressor. The compressor basically takes the gas that's in this system, it increases the pressure, and this increase in the pressure causes the refrigerant, the chemicals, to heat up. And then basically the heated chemical is going to flow through a series of pipes in this condenser region. Air is going to flow over the pipes and is going to cause the coolant, the refrigerant, to cool off, going from hot to warm. So basically cooling it down a little bit. And then it's going to go into an area where it's going to be expanded. And so we're going to increase the volume drastically. By increasing the volume, we're going to decrease the pressure without going into a lot of the math. It's one of the laws of chemistry. And that's going to allow the refrigerant to get very cold. And so that cold refrigerant is going to flow through another series of tubes. And at that point, if it's in your air conditioner, a fan is going to blow through this cold air, blowing the cold air into your room. If we're looking at a freezer, that cold air is going to add coldness, basically cold factors, into the refrigerator, and is going to help to cool it off, or into the freezer and help to form the ice. And that whole system then is going to circulate again. But all of that, again, is going to take these chemicals, which are potentially harmful to the atmosphere, and it's also going to require a lot of energy. Energy that we need to figure out a better source of, so we're not using the burning of fossil fuels and generation of pollution to power what we need throughout our lives. So this gets us to our ethical dilemma in science for this week. Is it ethical to drink ice water? Should we recognize the privilege that we enjoy through easy access to cold, clean drinking water? And then a sub question underneath that, how do we ensure that everyone has access to safe and clean drinking water free from microorganisms, bacteria, toxic chemicals, viruses, and fecal matter? So thank you for listening to this week's Ethical Dilemma in Science. As always, please see the description below for additional information and references. Thank you and have a great week.